Okay, let me share my screen here and hopefully it still works. We tried it earlier. All right. How am I looking there?
Looks good to me.
Okay, great. Awesome. Well, thank you so much for inviting me. I also have to mention that when I was a student at Carleton College, I did my first field research project in Wyoming, and Bob Carson was my first field advisor. And so Bob and I go way back, and it would be really cool if I could join on the 14th. I don't know if I can, but that would be amazing. He's a really great scientist, really great geologist. So. All right. Well, I know you guys are a club of ice age floods, but I want to talk to you about earthquakes. It's what I do and what I try to share with people. And I think there's really great stories about earthquakes out in Eastern Washington that a lot of people don't know. And so I'm really excited to be here to tell you about them. So I'm going to talk about earthquakes, why they happen, and how to be prepared. And I'm going to focus on the why a little bit, but I'm going to focus on earthquakes that don't get a lot of press coverage. And these are the ones that affect Eastern Washington, so it's a great topic for the people in this club. What I'm showing on my intro slide here is nice topographic map that one of my collaborators sent to me of the Wallula Fault Zone, which is going to be the star of the presentation. And you can see the amazing topography that forms along the fault. One thing that is a good take home from this image is that the faults are responsible for a lot of the beautiful landscape we see in Eastern Washington, especially in the Yakima area. And so knowing about them will also help increase your appreciation of the landscape. Okay, so to start, we're going to take maybe a couple steps back. I want to talk about what earthquakes are. And to get an earthquake, first you need a fault. So I'm going to talk about faulting and then we'll get back to earthquakes. So I'm going to use a word a lot in this presentation. It's a fancy word that geologists use. It's called deformation. And faulting is a type of deformation, but all deformation is a change in shape. And for faulting, it's a change in shape that happens when you break rocks and take one side of the rock and slide it past the other side. And I show in this picture many different examples of faults. In the center, you can see that faults can be small. They can be of size that you can just see on the ground, or they can be continental scale, such as the San Andreas Fault, the really famous fault in California. On the left-hand side here, you can see block diagrams from a textbook showing what happens when faults move. And I'm showing you two faults that happen predominantly in Washington. One is reverse fault. If you take the rock and kind of squeeze it, you end up shoving one piece over the other, and that's called a reverse fault. If you take one side and try to slide it past the other, you get something called a strike slip fault. And these are really common in Washington. So an earthquake happens when one side of the rock tries to slide past the other. So there's an attempt at deformation. But then the two sides stick together. And all of you should just take your hands and put them together and put a little pressure on them and try to slide one hand past the other. And you'll feel a little bit of deformation in your skin. You can feel it's kind of springy. That's called elastic deformation. We have a fancy word for that in geology, but it's just like, pulling on a rubber band. And as you try to slide one rock past the other, eventually the pressure becomes enough that it overcomes that stuck part and it slips suddenly. And that is brittle deformation. That's our word for it in geology, or breaking. And that's the earthquake. So if you think about the rubber band analogy, it's like when you stretch the rubber band, eventually if you let it go, you release all of this energy. So that's when the energy is released. And of course, when you're stretching the rubber band and shooting it at your brother, your sister, when you're a kid, it goes and flies over and flaps them in the face and then you get in trouble. But the rubber band shooting is an example of the energy and what it can do. It can move things, it can travel. And so that is the shaking that you experience during an earthquake. Okay, so you need a fault and then you have an earthquake. Okay, so what makes faults in Washington? Well, a lot of us have heard about the big fault, the one off the coast. And this is basically a really big interface between two tectonic plates. We have the North American plate, which is the one that we live on, and then we have the Juan de Fuca plate, which is just offshore. And the boundary between those two is called a subduction zone, where one plate is trying to slide past the other. And in this case, the Juan de Fuca plate is trying to slide underneath the North American plate. And we get earthquakes along this zone because as the Juan de Fuca plate is sliding down, it sticks, and then you get a slow distortion of the North American plate. And then eventually that sticking slips, you breaks, and then you get a movement of the fault into something near its original position. And so we make a big earthquake. This particular fault got a lot of press a couple years back because of an article in the New Yorker. I don't know if some of you saw this. It was called The Really Big One. And the article got some things right and some things wrong. I wanted to show you the image from the cover of the story. It's a little bit exaggerated. This fault does not extend from Canada to Mexico, as shown in this picture, but it is a really, really long fault. On the right is a map. You can see the pink area shows where the fault is, kind of extending underneath North America. It goes from off Vancouver Island down to Northern California. And a really important take-home point from this is that because it's so long, it can make a really large magnitude earthquake, because as it slips along that whole length, you release a lot of energy. It's gigantic rubber band. And so kind of the relationship is the longer the fault, the larger magnitude earthquake it can make. But this is not the only fault that exists in the Pacific Northwest. This is a block diagram showing, the tectonic situation here. And, if this interface between the two plates, if it slips and we get the big one, that'll be a disruption to all of Washington, including folks in Eastern Washington. But there are other faults that should concern us too. And one is that as the Juan de Fuca plate is going down into the earth, it's bending and it's deforming and it's breaking and it's creating earthquakes too. An example of this is the Nisqually Earthquake in 2001. That was this type of earthquake down in the plate, and those we call intra-slab earthquakes among us scientists. But then also, as these two plates are coming together, it puts a lot of pressure on the North American plate. And so the North American plate is also bending and breaking and yielding to that force. And so we get a type of earthquakes in Washington called shallow crustal earthquakes. And that's the type that I'm going to talk about the most today. And though this image doesn't show much of Eastern Washington, that doesn't mean we don't have earthquakes there. In fact, I'm working with one of the people in our publications group to redo this figure to show Eastern Washington, because it's important that we're all prepared throughout Washington for earthquakes. So I'm going to zoom in on that area and show you, but that's where we're going to focus our attention. So this is a map of Washington showing all the active crustal faults, these shallow faults that we know about. And this is an image I captured off the Washington Geological Survey information portal. And each of these blue lines, some are dotted where we're less sure about where they are, some are solid where we're really sure where they are. Each of these lines is a fault that could produce an earthquake. And you can see that there are indeed quite a few over in Western Washington, but there's a whole lot of them in Eastern Washington as well, in particular close in around Yakima. And this is an area that scientists called, you may have heard in a talk before from a scientist, a Yakima fold and thrust belt. So it's an area that is experiencing deformation. Now, one question that you may have is, why are there so many earthquakes out in Eastern Washington when kind of the source of the action is off the coast in Western Washington. So I have a really interesting story to tell you about that involves some data that I'm going to walk you through. Okay, so let's start in the upper left of this slide. We know about the deformation in this zone because, well, we can see it in the landscape, as I mentioned before, but we can also track it using GPS. And when I talk about GPS, it's the same system that you use in your phone. You might have a system that tracks your location in the car. It's a system for tracking locations. And instead of a small little antenna that you have in your phone that can move around, what geologists do is they drill a hole in a solid piece of rock and they stick a really stiff rod in there and cement it in. And then they can attach an antenna to it. And this is a picture of me working with some scientists in Joshua Tree National Park in California doing this kind of work. And you can see that the big white disc is the antenna that we use for scientific research, and it's really high precision. And so if we put this antenna on the rock with some computer to record the data, we leave it out there for about 5 days, recording a position every 15 minutes, no, 15 seconds, sorry, 15 seconds, then we can actually find out the position of that spot to a precision that is less than a millimeter. So that's less than 1/16 of an inch, much less than that. And then if we go and measure at that spot again and again and again over the course of many years, we can actually track how that spot is moving relative to another spot. And so we can actually track how little pieces of crust are moving, even though they're moving very, very slowly on the order of, millimeters or a fraction of a millimeter per year. And the result of all of that effort in the Pacific Northwest is shown in the map in the lower left corner. This map shows a bunch of arrows, and the tail end of this arrow is each one of them corresponds to a site that looks like that picture in the upper left. And the arrow head indicates the direction that spot is moving. And the length of the arrow relates to how fast it's moving. So it's all relative. And you can see a very interesting pattern popping out. So in Western Washington, you can see that the western coast is being crunched, and that's because of the subduction. So we already talked about that. But in Eastern Washington, Eastern Oregon, and Idaho, we see this interesting circular pattern, like this crust is kind of moving in a circle and around a spot that's located about where Spokane is. And the pattern has been a perplexing thing for geologists for a long time. Why is this happening? Well, one of the outcomes of this, we don't know exactly why it happens, but we've shown with the data that it does happen. One of the outcomes of this is that Western Oregon, which is a big, really, really strong, stiff block, is actually kind of rotating up into Washington. You can see that with the GPS arrows on the map. And on the right, you can see I've outlined with the circle, there are places in Western Washington and the Yakima Fold and Thrust Belt where the crust is being compressed north to south. And that's why we have the Yakima Fold and Thrust Belt. Now, this story isn't just told by the GPS data, it's told by the topography and the geology itself. This is an image that shows Washington. I'm sorry if it's a little light colored here. Hopefully you can all see it. Showing all of those faults that I showed in blue on the previous map are now shown in either gray or yellow. And I've highlighted a couple that are gray and one of them that's yellow. And what we see in the pattern of faulting is that the gray ones are mainly oriented east-west, and they're reverse faults. So they're a response to north-south compression that we showed with the GPS data on the previous slide. All of the yellow faults are this other type of fault, the strike-slip fault, where one piece of the earth is sliding past the other. And they're all kind of in these arcs that are parallel to those lines of rotation shown by the GPS. And so the Earth is actually deforming in a way that we expect based on the GPS data. And the fault orientations and types actually show this also. You can also see the rotational pull up by Spokane in this image. And so the the GPS, the geology, the topography, they're all telling the same story about this rotation, compression, and strike slip faulting. So what's really relevant to the Lake Lewis chapter of the Ice Age Flood Society? Well, it would be the strike slip fault that is highlighted with the yellow arrow in this diagram, which runs through the Tri-Cities, and it's called the Wallula Fault. So next I'm going to zoom in on these Yakima fold and thrust belt faults and give you some names for a bunch of the different faults. So you can see the Wallula Fault running in the Kennewick area, Tri-Cities area. There's also a bunch of east-west oriented faults that have names on them here. All of these faults are pretty long, and if you remember, long faults can create larger earthquakes. And so these are the faults that are of concern to someone like me who does research and wants to help people get ready for the next big earthquake, because these are the faults that could potentially create a big earthquake. And so we want to study them, we want to understand them, we want to tell people about them and get people ready. In addition, there are some faults up near Entiet. I've got a orange circle around those. Those faults I don't have on this map yet because they've just been mapped. And this comes from our information portal. And I'm actually in the process this fall of updating this map on the portal so that we have a whole bunch of faults that have been mapped in the last 5 years updated. So if you want to look at faults on the portal, you can go look at them after this talk. I'm going to give you the link and tell you how to find this. And you can look at the faults yourself, but do take a look in the spring. Put a little reminder in your calendar, look in the spring, because it's going to be a different map and more updated version. A couple of points that are important. Number one, two of the largest historic earthquakes, these are earthquakes that happened during the written history of Washington, happened in Eastern Washington. The first was the 1872 magnitude 6.8 earthquake up near Entiet and Chelan. And the faults that I mentioned that are up there that scientists have mapped were responsible for that earthquake. Of very important interest to you all in the Tri-Cities area is the 1936 magnitude 6.0 earthquake that happened. It was called the State Line earthquake, or there are some other names for it, but it happened just near Walla Walla. There were a lot of reports of damage in Walla Walla. And so that one is very close to the Wallula Fault. And so we're very interested in understanding the Wallula Fault in particular. So this is where the faults are that we know about. We're also interested in not just understanding where the faults are, but how often there are earthquakes on these faults. And so I'm going to highlight research in this talk about how often earthquakes happen to paint a larger picture of the earthquakes themselves. The turquoise diamonds in this map actually show the position of trenches. So this is where geologists have actually dug a trench into the ground across a fault to try to understand its history. So the diamonds are existing trenches, and that needs updating too on our server. There's actually one just west of Kennewick I'm going to talk about in this talk that isn't on here yet. But there's actually trenching that has been currently happening in both in the Ellensburg area, shown by the flag up in the northwest of this map, and also close to the Tri-Cities, east of the Wallula Gap. And that's the research I'm going to highlight here. So trenching tells us about when we could expect earthquakes to happen, or how often should we expect them. Now, this question in particular, I'm not actually going to answer today in full. It's kind of the million-dollar question in earthquake science. Understanding this would just be fantastic, but it takes a lot of work. And that lot of work you can see pictured here in this photo. So this is the work of Steve Engster. He's a researcher at the U.S. Geological Survey and one of my colleagues. And they went out and did a new trench in 2019. In the upper left, you can see a very high resolution topographic map of the region where they were trenching just south of Highway 12. So this is east of the Wallula Gap. And in this image, you can see stream channels, you can see Highway 12, but marked with the scarp and some arrows is this line in the topography. And this is a place where the scientists who were studying this, Steve and his colleagues, saw that there was a line that indicated that maybe the surface of the Earth had been offset. So the surface of the Earth itself had been deformed. And they were wondering if a fault was responsible for that. And so they went in and they dug a trench. They hired a big backhoe to dig a deep trench. And after they dug the trench, the next task is to go in and characterize the geologic deposits in the trench and map them out to understand the story that the deposits have to tell. And this is where ice age floods become actually really important to earthquake science. So actually, I was really excited to be invited to give this talk because there's a really great crossover in this story. So Steve answered to send this to me actually yesterday. I just got, this is like hot off the presses. He hasn't even published it yet. And I can tell by his figures, he's getting close to having a paper ready because they're really beautiful. But on the left, you can see a little documented photo of the trench. And he has marked the tushy beds are the deposits underneath, like in the lower part of the trench that they dug through. And then there's also Holocene loess on the top, so wind-blown deposits. And what they found within this trench was something called flame structures, which are labeled on the photograph. And these are structures where if you have earthquakes or some sort of jiggling of the deposits when they're wet and kind of loose, so it's you know, close to the surface, you can actually get liquefaction, which causes sand to liquefy and kind of shoot up through the overlying material. And so they found tons of these things within the trench. And of course, to make this, it's really common that earthquakes make liquefaction. And there was documented liquefaction during the 1936 earthquake. Now, what they were hoping is they would see an offset where the fault came up and offset these things and they could actually date the earthquake really precisely. However, they did not find an offset, and that's actually pretty common. If the fracturing and offset that created the earthquake happened a little deeper down, it didn't quite get to the surface, you can actually have deformation at the surface that involves folding. So you just kind of take the materials and you kind of tilt them, and you don't actually have offset near the surface. So they're expecting that that's what happened here. But they saw the folding itself and lots of liquefaction. It was very pervasive. And in the upper right-hand corner, this is a diagram, a very detailed diagram of what they mapped out in the trench. And you can see the tushy beds. Rhythmites are really beautiful. And then you can see the liquefaction in orange all throughout. And they actually also found fracturing associated with the folding that is in the little box. There are little red lines. They're a little hard to see probably if you have a small screen. But they dated the soil on top, and these fractures went through the soil, and they dated it as being less than 580 years old. And based on the array of evidence they have here, they think that this scarp was actually created during the 1936 earthquake. So what they're seeing is evidence for offset and movement of the Earth much farther northwest of where the reported earthquake in 1936 happened. In addition, there's existing work on the Wallula Fault to the northwest of the Wallula Gap. This is a picture from a quarry closer to Kennewick. And the same group of folks, Steve's colleague, Brian Sherrod, did some work out here. And their analysis of both trenching and quarry exposures in that area indicate 5 earthquakes since 30,000 years ago. And those are the black bars that are outlined in red in the time scale there in the center. So if we look at this, we can think, well, earthquakes, so we have one earthquake in 1936. This was also documented here. 4 other earthquakes since 30,000 years ago. So maybe earthquakes don't happen very often out here. So should we really be concerned about it? To give you a sense of comparison, in California, people are really concerned about earthquakes. Earthquakes happen a lot there. And for example, the San Andreas, it slips about 1 inch per year. So that's 1 earthquake every 150 years. And the Wallula slip rate, based on all of this information, is less than 1/16 of an inch per year, so much less. And that's only one earthquake every 1,000 years. So again, it's like, maybe we shouldn't be so concerned about it. However, this is just one fault and one section of one fault. So I'm going to kind of back out again and we'll look at the big picture. So one site may not show a history of all earthquakes on a fault. So even with these two sites, we may not have the entire history of that fault. And then hazard, so how this affects us, includes all faults that might affect an area. So the Wallula fault, though it's the closest to the Tri-Cities, may not be the only fault that we should be concerned about. So for instance, the Wallula fault, we've documented one earthquake every 6,000 years. But the Saddle Mountains fault, we've studied a lot, and that's one earthquake every 2,000 to 11,000 years. And then there's all these other faults in the region. So when you add them all up, we end up having, potential for a major earthquake out here every, 30 to 50 years is probably not as often as it would happen, but, there's a strong possibility of having one every 30 to 50 years, maybe 100 years. And that could happen in our lifetimes. So understanding all the faults is really important. The other big question mark, besides understanding that slip history or how often earthquakes happen on each fault, is understanding where all the faults are, and do we even know where they all are? And you can see that the faults up towards the Ellensburg area, kind of between the Tri-Cities and Ellensburg, the Saddle Mountains fault was one of those. You can see that they are lines that don't really connect to anything. And so there's a big question of where do the faults go off the west end of those faults? And what about as they continue east of Moses Lake, where do they end? We need to ask this question because faulted crust is like broken pottery. The fractures should continue until they meet one another. And until we understand that, map out that whole network, then it's likely we haven't found them all. And so there's still a lot of work to do for full understanding of earthquake hazard in Eastern Washington. And I would like to just say that a lot of the work that I do involves not doing the trenching like my colleague Steve does, but I go into areas where we don't know where the faults are and try to map them out. And I'm actually doing a lot of work right now in the Ellensburg area with one of our geologists to try to figure that out in that area. Okay, so if we had the total picture, if we knew all the faults, where they go, how they connect, and the average time between earthquakes for every fault, we could build a map that looks like this. This is the hazard map for the San Francisco Bay Area. So just like a weatherman produces a forecast of the weather, if we have enough information, seismologists and geoscientists can produce a forecast of earthquakes for a given area. So we have enough information in the San Francisco Bay Area that there's a 70% probability of a magnitude 6.7 or greater earthquake on that fault between 2000 and 2030. So we could actually produce a forecast for like that. And the map that you see here shows the breakdown for what percent we expect, what probability it is for each individual fault within the system. But in the whole area, there's still a 70% chance. And of course, we're pretty far past 2000. So, if we look at their most recent image, it might show an even higher probability. Now, I would love to have this for Washington, Eastern Washington, but it takes a long time to build up enough data to be able to produce something like this. I'm showing a picture in the bottom of the 1906 San Francisco earthquake that really spurred people to understand earthquakes basically, and also to start studying the San Andreas and associated faults in that area. So California had 100 years of research to get to this state where they're able to create this kind of forecast. And so we started studying faults in Washington, these crustal faults, only a few decades ago. So we have a lot of work to do to come up with something like this. But if I had my wish before I retired, I'd be able to do something like this. But we'll see if we get there. At least we'll get closer. That's what I hope. Okay, so we don't have a forecast, but for the faults we do know about, what do they mean for you? What do they mean for you in the Tri-Cities and for me in Western Washington? Let's talk about the other aspect of earthquakes, which is ground shaking. So remember our rubber band analogy? When you create an earthquake, you stretch the rubber band, then when you let it go, you release all that energy and the rubber band flies across the room. Well, the earthquake waves and the ground shaking is the effect that we feel, and that's from that energy. And depending on how far away you are from the source of the earthquake, so where the earthquake happens, the fault, and in this diagram in the lower corner, seismologists call that the focus or the epicenter. Depending on how far away you are, you'll feel the earthquake very differently. Just like if your brother shoots you at close range with a rubber band, it's gonna hurt. Whereas if you're way across the room, it might not even reach you. And another analogy is a light bulb, which I show in the lower right corner. If we think about the light bulb, the brightness of the light bulb is the earthquake magnitude. What's the energy at the source? Then the light that reaches you, if you're in a dark auditorium, you just have a single light bulb. The light that reaches you is going to be less and less the farther you are away from that light. And that's due to the dissipation of the light energy as it moves through the room. Well, the same thing happens with earthquake waves. That shaking dissipates the farther away you get. We have actually a very useful scale for this in science. It's actually what we call qualitative. It's made with words, which is, I think, really nice for people to understand earthquakes. It's called the Mercalli scale. And it's shown here on the right. And it uses numbers, true, but there's actually a description that describes what would actually happen if you had, say, Mercalli intensity 6, which is strong shaking. It's felt by all, many are frightened, some heavy furniture is moved, and a few instances of fallen plaster, slight damage. And so it's a really useful scale for us to understand as people living in earthquake country, what would happen if we had an earthquake. Though we can't predict when the next earthquake will happen, in places where we understand things really well, we have forecasts, as we showed for California. We can actually predict if we had an earthquake in a certain location of a certain magnitude, what would be the shaking we'd feel from that earthquake. And so one of the types of things that I work on in our public outreach is creating something called earthquake scenarios or shake maps. And what it shows is the highest potential strength of shaking in a given area due to a particular fault slipping. And so it's a combination of the length of the fault, so the magnitude of the earthquake, how far you are away from that earthquake, and a little bit like what kind of geology is in the subsurface of that area. So what I show on the left is an earthquake scenario or shake map for a magnitude 7.4 earthquake on the Wallula Fault. And it would happen if you actually fractured almost the whole Wallula Fault that we have mapped. That's a pretty big earthquake. Is that likely to happen? It's probably the maximum we'd expect. So remember, this is the highest that we'd expect. In reality, it might be much lower than this. However, if we did have this very large magnitude earthquake, we'd have strong to violent shaking in the Tri-Cities, which sounds a little bit scary, but it would cause damage to structures. It would cause objects in rooms to move around a lot. You might have pretty severe damage to buildings. But kind of reality is, if we think about the 1936 earthquake, which we think ruptured the Wallula Fault based on Steve's work and some of the other trenching. The 1936 earthquake was only a 6.0, and that caused moderate to strong shaking. So it was felt, you might break some dishes, move some furniture, but there's not very much damage. And so if we think about getting ready for an earthquake, or what do we do now that we know about these faults, we can kind of look at the maximum and get ready for that, but also maintain an expectation that if an earthquake happens, it's probably going to be in that moderate to strong range. So now that you know about this fault and that there are faults that are close by, what do you do? First, you plan. then you prepare, and then you practice. And some of these slides are put together with the help of the Washington State Emergency Management Division. We've done some talks around Eastern Washington, and we kind of tag team. So I stole these slides from them, and they're really nice. So they have a lot of really great earthquake preparedness information, and I'll put their links to their websites as I go through this information. So first of all, let's talk about planning. Planning means that you actually put together a plan for what you need to do. So make a list. That involves understanding what's going to happen. So if we look at the scenario and actual earthquakes that have happened on the wall of the fault, we would expect moderate to violent shaking, and you might prepare or make a plan that's different depending on what kind of shaking happens. Luckily, we don't have very violent or extreme shaking, so we escaped that section. But we should think about what happens with severe and violent shaking. And you'll notice in these descriptions that damage to buildings, and particularly poorly designed structures like what we call non-reinforced masonry. This would be brick and concrete and stone that hasn't had reinforcement attached to it, can actually fall down. Now, does that mean that if you're in an unreinforced masonry building in Kennewick during an earthquake, you should run outside the building because it might collapse? Absolutely not. Let's talk about that. So this is on the left, a map that shows a count of all the unreinforced masonry buildings across Eastern Washington. You can see Richland is marked there, and in that area, there's 95 buildings that are not reinforced. And so, that could be, you think about that, that could seem kind of scary to be in one of those buildings during an earthquake. But even in these buildings, you should definitely not run outside during an earthquake. On the right, I have pictured unreinforced masonry buildings that were actually damaged during the Nisqually earthquake. We have good documentation of that. And often what will happen is that the poor reinforcement, there's some reinforcement on the inside, but then there's nothing on the outside to contain the blocks. And so often what happens is that of the walls, the walls will kind of peel off and fall out into the street. So in this building, actually, the one pictured at the top, the proprietor of the restaurant at the bottom, he was inside the building and he ran out. And immediately after he ran out, he got into the middle of the street, and then that top half of the building fell down. So if he'd been running out at the same time it fell, it would have been bad news. So even if you're in one of these buildings, it's unlikely to fall down completely. And being inside the building is still better than being outside. So what do? You drop, cover, and hold on. Now, some of you may have heard when you were younger that you should get in a door frame or other advice. And research that's been done since in the last 30 years has shown that it's best to actually get under some sturdy piece of furniture that's close to you. First of all, ground's going to be shaking really hard. You're not going to be able to walk. So you want to drop because you can't walk. You don't want to injure yourself by stumbling when you're walking. So then you want to crawl to something like a table or something to get underneath and cover your head, and then hang on to that piece of furniture because the ground's going to be moving and the piece of furniture can actually walk away. So you stay in one place and the table moves off of you, which doesn't help. So that's why we do drop, cover, and hold on as the advice, because in reality, you can't really run anywhere when the ground is shaking that hard, or even walk. So here's an example of some kids. This is in a classroom in Alaska doing drop, cover, and hold on. And I hope the sound works. I guess we'll see, but you'll see the action anyway. I think they were recording this lecture, and these kids are great. They're fantastic with their drop, cover, and hold on. Beautiful. And in that video, you can see that the chairs and the tables were starting to move around. The lights went out because there was damage to the electrical, And so you couldn't see to try to get out. You might be caught in an area where you can't see and you're exposed to falling objects. So it's really the best to drop cover and hold on. Oh, all right. So a lot of us, if you've ever practiced during the Great Shakeout, which I'm going to talk about here in a couple slides, if you've ever practiced, a lot of times it happens during the day and maybe you're out and about and you can get under a table, but what happens when you're in bed? What do? What happens if you're in a wheelchair? How do you protect yourself? What happens if you're driving your car? It's good to think about what you're going to do in all those different situations. This is a great poster that Washington Emergency Management Division put together that shows what to do in these different situations. Like, for instance, they have a phrase: if you're in a wheelchair, you want to lock, cover, and hold on. You don't get under something. You just lock yourself in place and protect yourself so you don't roll and so that you protect your head. But we want to think about these things in different places. The one I like to highlight is being in bed. You just kind of lie face down and grab your pillow and put it over your head and just wait. Because if you try to get out of bed, you might stumble and fall. There might be breaking glass you could step on. And so it's best just to stay in bed and protect your head. So it's good to think about these things, and especially I'll highlight when we practice. Okay, so that's what we do if an earthquake happens. Now, how can you actually get prepared? That's an important part of getting ready for earthquakes, is preparing. And I'm going to highlight two sections. First is how do we prepare for moderate, strong, and very strong shaking? And then how do we prepare for that more severe and violent shaking where there might be structural damage to say, our houses, like if we're thinking about our own house. So let's talk about the moderate, strong, and very strong first. Okay, so this is what you don't want. If you don't like cleaning up messes, you should get ready for earthquakes. These are pictures of what happened to people's offices and kitchens during strong shaking during an earthquake. And you can see it just makes a mess, and you just don't want to have to deal with that. It's also unsafe because, heavy objects like our refrigerator can actually move and walk, and if they fall over, it can be a little dangerous. So it's really good to secure your house. And we recommend that people go on a home hazard hunt. If you have kids or grandkids, this is a fun thing to do, is to talk to them about earthquake safety and then have them go on a hunt in the house and find stuff that might fall down if it was shaking. And then you can take action to secure large items, make moves to keep books on the bookshelf by putting a chain across. One really important thing people don't always think about is water heaters, especially gas water heaters. If they fall over, it can break the gas line. And so you definitely want to make sure your water heater is secured. It can also be a source of water. If the water goes off and you need water, if you have a tank water heater, that's a good source for water that's already potable and ready to go. So definitely secure your water heater, but also other objects in your house. Okay, what about getting up into severe to violent shaking? How should you prepare, say, your house for this? Now, most of us these days live in a wood frame house. So if you are in an unreinforced masonry house, you should probably work with a geotechnical engineer to just check it out and see what needs to be done to secure your house. Maybe if you have a brick chimney or something like that. But actually for wood frame houses, it's pretty easy to secure your house in most cases. One of the most common ways houses are damaged, wood frame houses, as the earthquake's moving, because they're wood, they kind of bend, and so they're not going to fall down. It's very unlikely, but it could get damaged. And if you want to avoid really expensive repairs, it's good to do a little pre-work. In particular, what can happen to wood frame houses, if they're not attached to their foundations well, they can actually slide off the foundation or damage the foundation. And as I show in the upper section here, in the bottom, you can see some examples of how to fix it. And they're often really simple and not that expensive. Just involves putting in some rivets, drilling some holes, putting in steel plates to attach your house to the foundation. We have a really great resource that we put together just a year or two ago called A Homeowner's Guide to Earthquakes in Washington State in the cover is pictured in the lower right corner. If you're curious about how do you get your house ready for an earthquake, please check out our guide. I put the link at the bottom. And so if you watch the recording, you can go back to that. So some of the fixes for your house can be pretty easy, and it can keep from having really difficult damage to deal with after the earthquake. The other aspect to understand for really heavy shaking is knowing how and when to control your utilities. It's good to know where your water and gas shutoffs are. And also understand where the tools are to turn them off. There might be a lever, but it might be a bolt or something. One good technique is to figure out how to turn off your water or gas, and then just buy that tool that works and tape it to the pipe right next to the valve so that you can just grab it and turn it off quickly. One warning is for natural gas. If you turn it off and there's nothing actually damaged, the utility needs to come to turn it back on again. So you don't want to turn it off unless there's really damage. So you only do that if you smell natural gas or hear a hissing sound, or say your dial is spinning rapidly. So you should go and check, but don't turn it off unless you really think there's a leak. And then you would want to build a kit. So if utilities are disrupted, a lot of different services could be disrupted. And so you should be ready for 2 weeks to be on your own. And also if you travel, it's good to make your kits portable so you can toss them in the car when you travel across the state. Let's say you go to the beach, Western Washington, want to spend time out there. You want to make sure that you have the materials with you need to support yourself for a while if you can't actually drive back to your house, because roads can be disrupted. There can be power lines and things in the streets, so it can be difficult to travel after an earthquake. Some of the things to put in a kit, I would really encourage you to go to the Emergency Management Division website, which I give the link to at the bottom, to make your they call it the 2 weeks ready kit. And this is the example of the grab and go kits, the version that's portable. A lot of people think about food and water, but there are other things that you might not think about that they mention, such as medications, lighting, and of course, if in this kind of situation, anything that provides comfort might be very welcome. So if you see a kid drinking his hot cocoa, I think chocolate is a must have for any grab and go kit, but I'm a chocolate person, so that's what I have in my kit. Okay, so I think this is the last slide on preparedness. So one of the things you should definitely do is sign up for emergency alerts to get prepared. It's good to sign up for your local alerts from your city and county, as highlighted in the left there. I think this is the right system for the Richland Tri-City areas. It's called Code Red. Also, just launched in Washington 2021 is a new system called Shakeout. And it is a system that detects once the earthquakes happen, so it can't predict earthquakes. Once the earthquake has happened, it detects it before the waves get to you and sends a warning in advance of the shaking. And it can give you a few seconds of warning that the shaking is coming. And so I strongly encourage you to make sure your phone is enabled with Shakeout. And again, the Washington EMD link at the bottom shows you how to make sure your phone's set up to handle those warnings. I'm on the committee that is actually helping promote this in Washington, and we're gearing up to go all over the state for the next few years trying to get the word out about this system. But you know, with a few seconds, you can do a lot. You can find that sturdy object. You can you know, make sure you're if you're in the street, you're well away from a building. You can pull the car over so that you're not actually driving. You're just stopped on the side of the road before shaking happens. So that's another one you should look into. And of course, the last thing is practicing. I want to bring your attention to the Great Washington Shakeout. It happens every year in October. This year, it's on October 20th, 2022 at 10:20 a.m. So what you do is like set an alarm on your phone or put it in your calendar. And at 10:20 a.m., you just go about your day. And at 10:20 a.m. on that day, you stop for a minute and say, hey, if an earthquake was to happen now in the place that I am, what would I do? How would I drop cover and hold on? How would I prepare myself if I got a warning that shaking was coming? it can help you kind of mentally prepare in different situations about what you would do at that moment. You can register for the event. They love to get a registration because I like to see people participating. So definitely register for the event and you'll get like little reminders and sometimes interesting information leading up to the event. Okay, I'm come to the end of my talk. I want to kind of highlight a couple of resources. I think I have time to do that. On the right here are some of the, a couple of those I highlighted in my talk, but then a few others that you might look into, especially there's a new site that the Cascadia Regional Earthquake Working Group put together about earthquake insurance. I tend to get a lot of questions about that during talks. It's so new, I haven't actually gone through the site to figure out what's there, but they're a really good group that does good work. So check that out if you're curious about earthquake insurance. And I also want to highlight and show you on our webpage where you find the map with the blue faults that I showed earlier. On the left here is a picture of our webpage, the Washington Geological Survey. And we do have a section, the circle on the left highlights where you would find all our earthquake information and tsunami information. And on the right on our page is a geological information portal, that rainbow flag. And if you click on that, it will take you to this, which is our map with geologic information. And there's a section that's called earthquakes, and under active faults, you'll see that there's a seismogenic faults layer, and that will show you all the faults that I showed in the maps during this presentation. And it's nice because you can actually zoom in and it will show you in a particular location where we think the faults actually go through in a pretty good detail. So if you're curious about, you know, how close your house is to a fault, then you can go check out this map to see locations in a specific region. So I think after the end of this talk, you can go back and rewatch the talk to get all these links and check out information. But I also sent a list to Chris to put in the follow-up email with all these links so you can go look them up later. So I guess with that, I will take questions.
I have a question. This is Liz. My question is just around we have a lot of this like layers of basalt in our area, and I'm curious how that impacts how earthquakes are felt on the top layers.
That's a great question. Something I didn't get into too much with the earthquake scenarios is that when we produce those scenarios, and we know from earthquake physics that if you have harder rock, let's say your house is built or you're standing on harder rock, the waves actually pass more fast through that. They go through it faster. And so it leads to less shaking because wave energy kind of passes through really fast. If you have really thick layer of sediment that's loose, let's say it's a young material, it's not very compacted, the wave will move slower and it'll be a lot more shaking. So if you're curious about you know, your house and what it's built on, if you're built on basalt, that's a double thumbs up because that's a hard rock. If you're built on something really soft, then like river bottom sediments isn't a great thing to be built on all the time. It can be fine. But if you're worried about that, you can always hire a geotechnical engineer to come look at your house, and they'll look at the geology and tell you for your specific location, you know, what they think about your house, and then also give you recommendations on what you might do for your house to protect it against shaking.
Awesome, thank you so much.
I don't hear any more questions. I'm sure anyone who's lived in this area as long as I have must be thinking, gee, all of Hanford sits in a big river basin. You just described, I always thought the softer the better because it would just sort of jiggle like a bowl of jelly, but I just heard that that's going to make it more severe. That's just wonderful. Okay.
Yeah. Yeah, and you know, that's one reason that, you know, I like to be invited to come out and give these talks, because the more we know about it, the, you know, more we can understand and be prepared and talk to our representatives about making moves to make everything safer.
Absolutely.
But
Okay.
definitely being prepared in your personal life is something that's very easy to do. So that's the number one.
And of course, you can look at the picture behind me, and all of my objects of things I've collected all over the years are all on the wall ready to
Yeah, and
go.
up high.
And then up high. Yeah, exactly.
Yeah.
All right, I'll move you down to the floor.
This isn't our homeowner's guide, but something that's really nice is called museum putty. And it's like a soft material that you can use to like stick things down with. And then even if you have probably strong shaking, you'll probably hold it in place. That's a really good thing to try.
Okay.
Yeah. George, do you have a question? Oh, you're not me, or you're muted, sorry.
I had a question regarding the flame structures that were found in the trench there on Wallula, along the Wallula Fault. Did you see clastic dikes?
Yeah. I think the flame structures are just like a wider version of a clastic dike. That's kind of another word that geologists use for them.
And much younger.
Mm-hmm.
Yeah, and so to get those flame structures, the sediment would have to be saturated, correct?
Yeah.
Okay, all right.
Cool.
Anyway, thank you.
Yeah.
I spent a lot of time looking at the Wallula Fault and the probabilistic hazard analysis and things like that. So it was good to get a refresh on some of the new stuff coming up. Thank you.
Yeah, great.
Yeah, I have a question, Megan.
Yeah.
I'm an interloper from Spokane, and I wonder if similar activity is going on in a little further east.
This is a really great question. I actually gave a talk at Eastern Washington University where I gave something similar to this, but I focused on Spokane. I wish I could show you those slides.
Yeah, that's true.
One of the things to note is, when I was explaining why we have these faults, there's that rotational pattern. And the spot that the crust is kind of rotating around is actually in Spokane. That means that in Spokane, the rotation's very slow, much slower than in the Yakima area. And so there's actually a lower earthquake risk in Spokane because of that. Everything's just moving slower. You're not pressing on things as much. There is a fault that created a few earthquakes. I can't remember the dates. I think it was maybe 2001. There was some earthquakes
2001.
out.
I
2001.
just moved
Yeah.
here.
Oh yeah. And that was on a fault called the Lata fault. And that's a very short fault. It was a very small earthquake because that fault's really short. And that makes sense because it's in an area where everything is moving slower. But one of the things that I emphasize for the folks in Spokane is that if you had a large earthquake on something like the Saddle Mountains fault, which I talked about in my talk, that could create still potentially some strong shaking in Spokane. So still getting your house ready, doing your home hazard hunt, making sure your objects are secure is still a really good idea, even if you live in Spokane. I hope that helps.
Thanks.
Mm-hmm.
If that was the presentation that you gave about a year ago,
Yeah.
it's actually available on YouTube.
Oh, cool. Go look for it.
Okay.
I had a question.
Yeah.
I was wondering, I saw that some of the fault lines ran along like near I-90. Is there anything that we could see visually that would indicate where those would be for those of us just traveling along?
Yeah, that's a really great question. So if you look at a topographic map of Eastern Washington, you can actually see the Yakima Fold and Thrust Belt on the topographic map. There's all these linear hills that pass through the area are associated with individual faults. And so actually every time I drive through the Tri-Cities, I'm looking at all of them going, hey, look, there's another fault along that ridge and there's one along that ridge. So pretty much any of those linear hills that you see, those ranges have a fault that is responsible for lifting that up. And that's where the active faults are. So next time you're driving through, just have a sense of wonder and look at those ridges and say, hey, look, there's geology at work, right in front of our eyes.
I love notches on car roads nowadays, but yeah.
Mhm.
Thank you. This was wonderful. Thank you.
Great.
Any other questions, folks? Well, Megan, thank you very much. It was a little disconcerting because I actually never really thought about earthquakes in this area. I always thought that we were sitting on this big stable table of basalt, but
Mhm.
more concerned about the next big flood, I guess. But thank you, and I think we could all do well to look around, and I know the first thing I'm going to go do is figure out where my water shut off and my electrical shut off is. Make
That's
sure I
right.
have the right tools. All right, thank you again.
Yeah. Yeah, when I talk to students and teachers, you know, the best way to lower fear and, you know, once you have this surprising information is to get ready. And then you feel more confident and prepared and know what to do. That just goes a long way.
Thank you again.
Yeah.
Okay, folks, our next meeting will be with Vic Baker in November on the second Tuesday, which I believe is actually the 8th of November. I'd have to go back and look at my notes, but I think the second Tuesday is the 8th of November, and same time zone.
Yep.
We'll have from your PhD stomping grounds, we'll have
Yeah.
Vic Baker talking about mega floods on Mars. It should be pretty interesting. Thank you.
Might have to attend that one.
Okay,
Mhm.
thanks all.
Thank you so much.
Hang on, Liz, I need to talk to you.
Okay.